New girl. Okay. All right, and Ashley. Ashley, honey, here you go. Here's the quiz. All right, friends. So I'm on page 30. Everybody's on page 30. Okay. I want to take a quick stroll through the last 8 days of your life in AP Calculus. Wait, it's only been 8 days. It probably feels like longer. I know, time flies when you're having fun. Just like, that's not what's happening. I feel like I die every day. Okay. When we first came in, the first 4 or 5 days, it was review. It was all review. Kevin, are you okay? It was all review of limits. We talked about limits. What does a limit mean? A limit means, like, as I get closer to this particular x value, what are the y values doing? Everybody okay? We then encountered that there are 4, count them 4, different reasons why a limit doesn't exist. I'd love to hear from some of you all, what are those reasons? There are 4 reasons why you would write a limit doesn't exist. Delia's got 1, Kevin's got 1, Roberto's got 1. There are a total of 4. Roberto, give me 1.
Oscillation.
Because of oscillation. Oscillation really means... that was the sign of the cross? What was that? Oscillation, we're wiggling, right? The functions I want to think about when it comes to oscillation? Not sin. Sine. Sine of x and cosine of x. What we talk about with oscillation, we're thinking about at the ends. As you approach infinity, you're oscillating. Limit does not exist because of wiggling, oscillation. Second one, Abraham.
Domain.
A domain restriction. What do you mean by a domain restriction?
If we ask, like, for example, as x approaches 1 from the left, but there's no, like, nothing coming from the left.
What do we think about a problem like this? Limit as x approaches 0 from the right of the square root of x. Domain restriction?
Yes.
Can we find this limit? Think of the graph. What does the graph look like? The graph looks like that. What's the limit as x approaches 0 from the right? Here's 0, come in from the right. You can find that limit is 0.
Oh, but if it's coming from the left.
If you said limit as x approaches 0 from the left, Jackie, what would be the problem there? There's a domain restriction because there is no graph. There is no graph to the left of 0, so this is a domain restriction. Okay, so we've heard, what was the first one? Oscillation. The second one, domain restriction, Carlos?
Unbounded behavior.
Unbounded behavior, what does that mean?
That infinity.
Your y values are approaching positive infinity or they're approaching negative infinity. We're okay with that, Pedro? There's one more. It's the one you knew for sure before you even met me. I see a lot of people doing this thing. Delia, what's this thing?
The left and the right don't equal each other?
The limit from the left and the limit from the right are not equal to each other. Ashley, you're okay? Okay, so those are the 4 reasons why a limit doesn't exist. If that's not happening, then the limit exists and you plug in and you build a table and you algebraic manipulate and all the things. And everybody's good? Okay, good. So that's our base. These are the skills. Now we start applying these things. And the first place we apply limits is with continuity. We've looked at continuity for the last 2 days. One of the things that you guys know about a continuous function, if you see a continuous function in front of you, a continuous function has no holes. Fancy word for hole? Removable discontinuity. There can be no
Jumps.
no jumps.
No.
The parent function I want you to think about for a jump discontinuity? Absolute value of x over x, so I should probably do it this way. This is a jump discontinuity. There's 2 other discontinuities. Breaks. We don't really have a parent function that does that, but you have like graph here and graph here and nothing in between. And then the last one? Don't just say asymptotes, because there's 2 kinds of asymptotes. It's the vertical asymptotes, that's why we do this thing. Vertical asymptotes. Everybody good? Seeing the graph, piece of cake. Proving that the function is continuous, that's tonight's homework. In order to show a function is continuous, 3 things. First, that you have to like prove, you have to write. What do you do?
Define.
The function is defined, meaning that there's a point on the graph. The second thing,
That it equals each other.
that those limits are equal to each other. Limit from the left and the limit from the right. But here's where you're going to be careful about them. You might have the function defined at a point. You might have the limit exists and still not continuous because maybe you have a hole and you have a point. So Kaylin, what's that last thing? Whatever that limit is, better be equal to how the function is defined. And everybody's good? Good. All right. So new application of limits coming. This is going to be something called the intermediate value theorem. You've not ever heard me use the words intermediate value theorem. But oddly enough, I know you know this. Trust your gut. What I want you to do is on page, what did I say this was, 30?
Yep.
Okay, there are 4 questions that I want you to explore with somebody near you. So, question number 1, let f be a continuous function. Let's just annotate this a little bit so that you guys are set up for success. If I say a continuous function, you know already, no holes, what else?
No jump.
No jumps, what else?
No break.
No breaks, what else?
No vertical axis.
No, is it okay if I just abbreviate VA?
Yes.
Okay. If you have a continuous function for all values of x, this says if f of x is greater than 0, well, f of x greater than 0 means y is greater than 0 at least once. That just means that there's a point above the x-axis. If you were to look at the graph, you'll see a point above the x-axis. And f of x is less than 0 at least once. There's a point below the x-axis. Does it have to be true that the graph will have at least one root? Last class there was some confusion. I said root here, and I think they thought I meant square root. What's the root that I mean here? I mean like zeros. Maybe you know this as x-intercepts. The question is, could the graph of x, does the graph of f of x have to have at least one root? Could it have more than one? Take a minute, discuss, I'll be back in a second. If you think it's true, give me a sketch. Delia, is the camera doing okay?
Yes.
Okay, good. Okay, some people have got a little sketch going. Not a bad idea.
No jump, no breaks, or vertical
All right, Mavericks, let's pull this together. F is a continuous function for all values of x. F of x is greater than 0 at least once. F of x is less than 0 at least once. Does it have to be true that the graph will have at least one root? How many of y'all would say this is a true statement? Carlos? Okay, how many of you guys think it's a false statement? How many of y'all have no idea? Be honest. That number should add up to 17. One more time. Okay, how many of you think this is a true statement? 1, 2, 3. False statement. You got to decide, friends. And how many have one person? 2, 3? Okay, hold on, wait for it. And then have no idea. Okay, that looks like it's going to add up to 17. So here's what I might do. Sketch a little graph. I know that the function is continuous, so no holes, no jumps, no breaks, no vertical asymptotes. There is at least one time where I'm up above the x-axis, and at least one time where I'm down below the x-axis. Does there have to be a root?
Yes.
Look at that. Doesn't it have to be true? Is there any way to draw a continuous function no holes, no jumps, no breaks, and get from this point to this point without crossing the x-axis?
No.
Right? There's no way to do that. So this statement is true. This guy over here would be the root. So the first part is going to be a true statement. That's all I'm asking for in these. Okay? Is it true or is it false? Now, the second part says, could the graph of f of x have more than one root?
Yes.
Could it possibly be that you go from this point to this point and you have another root?
Yes.
What would that look like, Jose?
It would go up.
Okay, we got a point down here. We got a point up here. What could it look like?
Like a sine graph.
Oh, maybe like something like that?
Yeah.
Everybody be okay with that?
Yes.
How many roots?
Very true.
Careful. 1, 2, 3. We're good? Okay, keep going. Try the next one. See what you can do. Yeah. Read it carefully. Last class, some students were convinced that I'm getting old, and I asked the same question again. Aren't you still in the list for missing stuff? Right, oh, but you're going to commit. Read this question carefully. Too many people think it's the same question. For all functions f of x that satisfy the condition f of x is greater than 0 at least once, and f of x is less than 0 at least once, the graph of f must have at least one root. Okay. Time to commit. How many of y'all would say this is a true statement? 1, 2, 3. How many think it's a false statement? 1, 2, 3, 4, 5, 6. How many? 7. How many of y'all have no idea? Be honest. Always thank you for the honesty. Fire did not just rain down from the sky. It's okay if you're not sure. So let's start with the sketch. What do we know? There's a point above and a point below. Does there have to be a root? Is it possible to go from here to here and not have a root this time? Abraham, why are you so sure?
For example, a parent function 1 over x.
Okay. The parent function 1 over x does something like this, right? I'm kind of drawing it a little exaggerated. There are points above the x-axis. There are points below the x-axis. Are there any roots? There's no roots. So it's possible. There's another parent function I was hoping somebody was going to think about. Naomi.
Absolute value of x over x.
The absolute value of x over x does the same thing. Negative y values, positive y values, no roots. The difference between question 1 and question number 2, right? You're not promised, let's just make a note, not promised continuity. All right, with that said, try number 3, see what you can do. These are going to get harder, but they're getting harder for a reason. We're building to something. Ashley, you okay? And this time. Nice. Now I'm starting to see some graphs coming to life here.
What about negative 2? Maybe?
We've got a continuous function crosses the horizontal line y equals 5, just for some dramatic effect. I'm going to add the lines there, y equals 5, y equals -3. Must there be at least one point on the graph such that h of x equals 2? That's the same as saying y equals 2. Does there have to be a place where y is equal to 2?
Yes.
You've got a continuous function that passes this line somewhere and passes this line somewhere else. If I look at the line y equals 2, could you get from here to here with a continuous function and not cross the line? There's no way, right? No matter how you try to draw it, you eventually have to cross. Okay? So what do we think? H of x equals 2, we're going to say that's a true statement. What about h of x equals -2? Lower that line a little bit. Is this also true?
Yes.
Okay, good. H of x equals -2 is also true. Last one, h of x equals -4.
Yes.
Yes.
Yes, it's true. You look like, you're like, no. What do we know? We know we pass through the line y equals 5. We pass through the line y equals -3. Jackie, what do you think about y equals -4?
I say yes because it's continuous, it's going to be continuous, it's an eventual extension.
Okay, so I'm going to draw this line y equals -4. Jackie, what I heard you just say is, yes, the graph has to cross this line because the graph is continuous. Everybody okay with that?
Yes.
Does everyone agree? No one wants to disagree?
I want to.
It's just me wanting to disagree here?
What if it doesn't, like, what if it's like approaches but doesn't touch it?
So you want to disagree with yourself.
Yeah.
You're a woman in conflict here. You've got, you pass through the line y equals 5, you pass through the line y equals -3, you have a continuous function. Is it possible to draw a function that does that and it doesn't cross this line?
Yes.
What would it do?
It would just approach.
It would approach, so like I hear you kind of thinking like asymptote behavior. Could it approach and be like, nah, and go back up?
Yes.
All those things are possible. I know, woman in conflict. So h of x equals -4, we're going to say is false. If you are mostly okay with this, Juan, you okay? Juan, you look like you're having some way deep thoughts. Somebody help him out. He went way too deep. Jackie.
Okay, so why can it not cross -4? But like when you draw y equals 5, you're crossing some part.
The difference is I told you it has to cross y equals 5. And it has to cross y equals -3. That's what I'm telling you. I'm asking, does it also have to cross this line?
So would it apply the same if you're asking for 6?
If it was the line up here, also. Perfect. Jackie, that is exactly what I was hoping we were going to get to. Whew, thank God. All right, so here it comes. Can I get a little drum roll, please? This is our first named theorem. I will tell you, in the world of AP Calc, there's only 4 or 5 named theorems. Only 4 or 5. This is one of them. This is called the intermediate value theorem. I want you to put a star next to this one. This one, it's big. It's our first one, but you already know it, and your ability to answer the last 3 questions tells me you know it. So give me a second to just read through this. We're gonna make sense of this with a picture. Suppose that f of x is continuous. Well, you guys know what that means. No holes, jumps, breaks, or the other thing? Vertical asymptotes. Vertical asymptotes. On AB. AB, we're going to call this a closed interval. A closed interval just means this, Beto. When I say the function is continuous, it doesn't have to be continuous everywhere. It has to be continuous from a point to another point. Henry, last period, had this brilliant comparison. He was like, oh, it's like the camera. The camera doesn't see the whole class. The camera sees from a point to a point. We get the point? Yeah, I mean, congratulate Henry. It was brilliant. Absolutely brilliant. So if I have a continuous function on this closed interval, And M, we're going to talk about M, is any number between f of A and f of B. Yeah, we're going to talk about that as well. Then the IVT says there exists a number C such that A is less than C is less than B, and f of C is equal to M. If that makes no sense right now, stay with me. Stay with me. Let's draw a picture. There's some markers in the middle of the table if you want to get like a really pretty picture. I want you to draw any continuous function. You want to get all sexy and exotic and it does something like that. That's great.
It can't have zeros?
I never said that.
Oh.
Any continuous function on a closed interval. So my closed interval is here from x equals A to here. Not there, I don't like that. Here, x equals B. Okay. Function is continuous on a closed interval. I think we're all okay. Here's A and B. The function's name is f of x, and we know that f of x is continuous. Okay. Let M, still haven't unraveled the mystery of M, be any number between f of A and f of B. F of A and f of B, these are y values. Specifically, you find them by, say, here's x equals A, go up to the curve and go over, here's f of A, whatever that y value is, f of B, here's f of B. I've got a point and a point. What's so special about M is that M is in between f of A and f of B. Anywhere in here is where M lives. So maybe I just want to say, here's M. What the intermediate value theorem says is this. There has to be a C, and C is in between A and B, such that the function evaluated at C is equal to M. Hold on, let me draw a picture here.
So they're gonna meet up.
They're going to meet up. They have to be equal to each other. If this line over here is y equals m, is there a place where the function and the horizontal line meet up?
Yes.
Does everybody see it? The intermediate value theorem says if f is a continuous function on a closed interval, and you pick your m in between here, there's always going to be a place, x equals c, c is between a and b, where the y value is equal to m. This is the intermediate value theorem. This is exactly what we were just talking about. Is everybody kind of okay? For your first pass through, if you're like, maybe, it's all right. Now, here's the thing. We're going to call this, it's called an existence theorem, E-X-I-S-T-E-N-C-E theorem. It's called an existence theorem because, Naum and anybody else, all that the theorem says is C has to happen somewhere in between here and here. Pedro, I'm not saying it happens at this place. All I'm saying is that it's somewhere inside the interval that it's going to happen. Is it possible that there's more than one place?
Yes.
Right? Imagine your graph doing more sinusoidal stuff, crossing a lot. Pretty good? All right, let's look at one sample AP question, and then you guys are going to get some practice, and I think you're going to totally figure this out. You're doing so much better than second period, which is why I'm so thrilled I got to film again. All right, all 5 of these questions have shown up on AP exams in the past, and I want these to be easy questions that you feel good about yourself with. There are plenty that you won't feel good about. These should be the ones you do feel good. All right, first one. We've got a function g, it's continuous. Okay, no holds, no jumps, no breaks, no vertical asymptotes. One. Somebody please take care of him. G of -4 is equal to 2. G of -1 is equal to -3. And G of C equals 0 once and only once. Here's how I might approach this. I know what the word continuous is. It means g of negative 4 equals 2 and g of negative 1 equals 3. Well, that's a point negative 4 comma 2. And that's the point negative 1, negative 3. Everybody okay? They're just points. Give yourself a little sketch. Here's the point negative 4, 2. Don't get all OCD and make it perfect. It doesn't have to be perfect. Negative 1, negative 3. I've got a point up here. I've got a point down here. I have a continuous function. They're saying that g of c equals 0. Another way to say this, you have a root. How many roots do we get? One root. What is the value of c? We've got a point up here. We've got a point down here. And the graph has a root. Do we know anything about c? What do you know?
It's between negative 4 and negative 1.
Why?
Because
You're 100% right. Go with it. Why does that root have to be between negative 4 and negative 1?
Those are x values.
the x values.
I've got a point and a point.
Yeah. So it has to be between those.
The graph has to do, would we agree, something like that?
Yeah.
Because we have a continuous function going from a point to a point. So there has to be a root somewhere between x equals negative 4 and somewhere between negative 4 and negative 1. This is where the root has to live. Could there be a root out here?
No.
Why not, Roberto?
Because there's 2 limits. Not the 2 limits, but the 2x value that they're asking.
Well, the other thing is they told you something about the function.
There's only 1.
There's one. There are no others out here. There's no others out here. Eric, you still with me there? Hi, Eric. So there has to be a root somewhere between negative 4 and negative 1. So the answer choice? Negative 3. Done. This is what the IBT theorem questions are going to look like and feel like. Take a couple minutes, see what you can do. Keep your neighbor awake here. You know, it would be inappropriate for me to start like punching you in the arm or slapping you on the face. But if I'm on that side of the room, I won't see what these gentlemen do here for extra credit in AP Calculus. They're just like, I'm going to get an A. Whatever it takes, that's what the poster says. Here. Suck on those. Get some energy. I don't give students demerits for falling asleep in class. I give it to the people sitting next to them. Background man.
Oh, excellent.
They don't wake him up.
That's the reason.
Roberto's thinking about moving back to his Punch him?
What does he use? Do whatever you take.
Actions are good.
The 3 or 4 is negative 4. So that's 2 is 1. So 2 points. You have to write C. So tiene que estar así. 4 is
Okay.
It's like you're holding your brain. No puede ser 5.
Tiene que ser.
Puede estar acá afuera. No puede estar acá afuera.
1, negative 1. 3, negative 2.
Positive
points. Now you got to figure out what K is. I don't know what K is. But I know that the x coordinate is 0. Oh wait, I don't agree with that.
Ya está ya más limpiado.
negative 1 and negative 2.
I did that.
All right, friends, time to commit. How many of y'all are going to go with A? B, C, D, E,
All I know
no idea. Okay, Beto, what have you done so far with this one?
I did a little drawing.
You made a little drawing, like an emoji? Or hopefully something more specific. Okay, I saw your drawing, and you've got the point 1, negative 1, which is over here. You've got the point, oh my god. Ay, Dios mío. 1, negative 1. We've got the point 3, negative 2. We've got a continuous function. And the question is, what do we know about k? What has to be true so that w of t equals 0 has 2 solutions? Where do you put this point 2 comma k so that you have to have 2 solutions? If you said 2, negative 2, that puts the point down here. Do you have to have 2 solutions? Do you have to have 2 solutions?
Yes.
If the point is down here, I could do a graph that looks like that, and never, ever, ever is w of t equal to 0. So it's not A. What if I move the point up a little bit, and I put it here at 2, negative 1? I still don't have solutions. What if I move it up more? 2, negative a half? No. Some people are arguing, there. Why not? Could it be that the graph does that? One solution. But as soon as you move that point up here, you get a solution on the way up, you get a solution on the way down. 1, 2, bada bing. It has to be E. Okay, keep going. Your brain's going to snap to this. It's going to be okay. Yeah. 1 is an example of what the K could be. Out loud, son. Your bench. There is some real power in these sketches. Very good idea if you do sketch. Okay.
I have a question.
Hey, man.
Okay. So,
I'm not going to say it's Carl. Okay.
so when it says a lesser versus, like when it's saying it has to be in between, it's only talking about the x, right? Correct. So that's why the y was 1.
Correct.
Okay.
Yeah. It's all going to come together. Once you think you've got number 3, call me over.
How are you going to have 2 solutions if you're not going to give you a positive?
Eso es lo que más nos está buscando. Es x. Estamos buscando en 3. Que es igual a.
Okay, so you already have a solution 7. So 7 is already a solution. It has to be 0.
Puede ser la A, pero no puede ser B.
Because it's already teaching negative 7.
What do you think?
Yeah.
So, Mr.
Yep. I'm listening, Jackie.
This, I drew the graph.
Yeah.
I haven't second that. But anyway, so it says that f of x equals negative 7. So
Yep.
doesn't that already count as a solution?
Okay. Friends, I want to pull everybody together. Sorry, Kevin and Jackie and all the other friends. So everyone seems with confidence to be doing something like this. Here's the point, 0, negative 10. And we've got this other point at 1, negative 5. And we've got 2 comma k and we don't know what k is. It's a lot like the last question, but a little bit different. Okay, what's different is the equation f of x equals negative 7 has 2 solutions. Well, f of x equals negative 7 is a line. Y equals negative 7. Here's the line, y equals negative 7. The function is continuous. Already, without even putting in that other point, is there anything we know for sure?
You already have one.
There's already one solution here. There has to be if the function is continuous. Has to be. The question then is, what's the just right value of k to get another solution? Is it 2 comma 0?
No.
Is it 2 comma negative 8? Right? Because if that's true, then you get that second intersection point on the way down. Jackie?
So basically, when it says f of x equals negative 7, you have to treat negative 7 the y as your like origin, right? Not origin.
Not, it's a horizontal line. Y equals negative
Well,
7.
like at the original problem.
I think a little bit, but not completely. I think we're kind of figuring this out. I want to leave the multiple choice. We're going to go over to the free response. This is going to be a little bit of a push, but you guys are going to be okay. I know you're going to be okay. You're in good hands. No crying in calculus class yet. Crying's coming, don't worry. That's how I'm going to get a fill up on my water bottle. Okay. So, free response. When it comes to multiple choice, Beto, here's the good thing. No one actually looks at your notation. No one looks at the supporting work. Jose goes through in the multiple choice, bubbles B and it's right, and C and it's right, and A and it's right. Great, fabulous. Free response, we are ruthless. I am the most ruthless of all. I have wicked high expectations. Your writing has to be precise, like all that limit stuff we did yesterday. So let's look at how you're going to handle an intermediate value theorem question on the free response. Eric, can I get you to read what step 1 is?
Show that p of x equals 4.
No. Up here where it says step 1.
Continuity state or prove that the function is continuous on the principle of
I swear it's on your paper. You don't have to do the long distance read.
the inference and how you this to be true.
How you know this to be true. You have, if you're going to use the IVT, Kevin, you have to convince me that the function is continuous, because the IVT is for continuous functions. The second thing is we're going to check out the endpoints of the function, because remember, those are the y values. Those are really important. We establish how high and how low. And then the third thing that we look at, think about all these problems we've done, is the value that I care about, is it in between? Everybody good? All right, so here's one. Show that p of x equals 4 sine pi over 4x minus 2 has a root somewhere in the interval. Does anybody see the words intermediate value theorem here? Sadly, no. They're not that kind. Neither am I. Show that this function has a root somewhere in the interval. Maybe you're thinking, gosh, this kind of sounds like IVT stuff. If we're going to use the IVT, the first thing you need to do, convince me that you know the function is continuous. I need somebody to convince me. Look at that function. Is there anything anybody knows about this function that you know this is continuous? Abraham's got some thoughts. Jackie's got some thoughts. I don't actually care about oscillation. I don't want to hear oscillation. I want to know how you know it's continuous. Pedro, do you have some thoughts there? There's a parent function here. The sine of x, right?
Yes.
If I asked you guys on the side to sketch out y equals sine of x passes through the origin and does that, right?
Yes.
And keeps going. What do we know about sine of x?
Continuous.
Continuous. This guy's continuous. Nice. Well, why does that mean that this is continuous?
Yes.
Why? 4 sine pi over 4x minus 2. What does the 4 do?
Just moves it.
Careful. What does the 4 do? It's a stretch. It's a vertical stretch. Does that stretching change continuity?
No.
No. What about this pi over 4?
Is the weight? No.
It's the width, right? It either compresses or it expands. Will that change continuity? What about that minus 2? It's a shift down. Does that change continuity?
No.
So what we know, I'd say this. Y equals sine of x is a known continuous function. Known continuous function. So P of x is also continuous. Check. You've convinced me. Eric, I know you know it's a continuous function. Everybody okay? We're continuous. Now, continuous where? Is this continuous everywhere? Is it continuous just on an interval? Okay, and the answer is, first of all, it is continuous everywhere. Right? This function goes on forever in both directions. I don't need that. What I need is continuous on the closed interval -1 to 2. Do we have that?
Yes.
Okay. So P of x is also continuous, and I'd say, I shouldn't have put a check mark there, my bad. On the interval -1, 2. So here's the thing. Continuous function on a closed interval. What I'd want to see here is then, so the IVT applies. When I say that word applies, it just means I get to use the IVT. Continuous function, closed interval, use the IVT. Check. The second thing is we look for the endpoints. Well, when I say the endpoints, what I mean is you're going to evaluate P at -1. You're going to evaluate P at x equals 2. You're going to plug them in. Plug them in. Well, let's do that. 4 times the sine of pi over 4 times -1 minus 2. Now this is a little bit mean, because now I'm hitting you with the trig. Trig, exponential, logs, all the time. Pi over 4 times -1 is negative pi over 4. The sine of negative pi over 4. Anybody know the sine of negative pi over 4? If you're not sure, go back to the unit circle. Go back to that unit circle on the side. First of all, what quadrant? 1, 2, 3, or 4? Negative pi over 4. Negative pi over 4. This one. You're down here in the 4th quadrant. The opposite side is the sine. It's negative square root of 2 over 2. So we've got 4 times negative square root of 2 over 2 minus 2. And before you totally freak out on me, 4 times negative square root of 2 over 2, the 2's cancel, we're going to get negative 2 square roots of 2 minus 2. P of 2, let's do this a little bit faster. 4 sine, trust me, we're going to do so much trig, it's going to flow. Pi over 4 times 2, pi over 2, or half of pi. Where is that on the unit circle? Here's 0. Pi over 2. Go straight up. What's the sine of pi over 2? 1. So this is 4 times 1 minus 2, which is positive 2. Last class had a little bit of a freak out, I think. Okay. Why does there have to be a root? Based on what we have here, why do we know there has to be a root?
Because it crosses positive and negative.
I heard something about positive and negative. If I think about this as a point, this is the point -1 comma -2 squared root of 2 minus 2. I don't even know what that number is. But you know what I know about this number?
Negative.
I know this is negative. I know this number is positive. This is a point -1, like if I've got a little graph going on here. -1, some negative number. +2, +2, guess what? Has to be continuous? I'm sorry, there has to be a root? But here's the thing, this is the write-up. The graph doesn't count. Here's what you need to do. Since, talk to me about the endpoints. P of -1 and P of 2. What we're comparing it to is the number 0. I need a root here. P of -1 is less than 0, and 0 is less than P of 2. What you just said here is, hey, 0, it's in between. It's in between these numbers. Since P of -1 is less than 0 is less than P of 2, there exists, means there has to be, a root between -1 and 2. And that's all that we wanted. We just wanted to know that there was a root. We didn't find the root, we proved that there was. These are going to be long to write, for sure. Is everybody mostly okay? I want you to have a really good model to look at. You're not going to do any homework on this tonight, but let's push a little bit further. I wish I had made it here. All right. Bottom page 32. Suppose the function v of t is continuous on the interval 1, 7, and the data is given in the table below. What's the minimum number of zeros that v must have in the interval? Take a minute. Trust your instincts. Do what you need to do, Jose. Trust your instincts. W is continuous on the interval 1, 7. What's the minimum number of zeros that V must have? It looks like some people are plotting some points. Great idea. Some people are just able to scan the data and they know. Okay. Show me in your fingers, please. How many roots? What's the minimum number of roots you think? Don't look around. Just don't do that. I saw you. You're like, what are the smart kids holding up? Okay. 3, 3, 3. Ashley's 2. Abraham 3. Trying to figure out. Did you just give me one finger? What just happened there? Okay, 3. We all seem to be pretty consistent with 3. Where's the first one?
Between 1 and 3.
In between 1 and 3, I have a negative endpoint, I have a positive endpoint. There has to be a root. The next one? Between 3 and 6. And then the last one?
6 and 7.
Between 6 and 7. I think we're good. Tomorrow we're going to focus on the write-ups. Tonight's homework is continuity. Nothing to do with the IBT. Continuity, continuity, continuity. Leave your homework in the middle of the table. Make sure your name is on it. Be kind to people. And if your name is in blue, I'll see you at lunch. So remind me, what was the conversation we had? I feel like we made a bargain. Did I just say forget about that one? We're just going to keep it as missing, and you're going to move forward. Okay, no, you don't need to worry about coming to lunch. We did what did we settle? Yeah. Okay, and did it have your name on it? It did. Okay, I get you taken care of. What's that? No, that's fine. Kelly?
There's something I
Okay, just write a little note that we did those other ones on the sheet. Hi. Good names. I have until Monday to get this taken care of. Hi! Wait, who's your sister? Ortiz? You know.
It's only being posted on YouTube, so we're going to keep posted on YouTube.
It's okay. I already have a YouTube channel. Okay, and I'll do it on subsheet paper. Oh, I need to get calculus time. You have yours? Thank you.
Alright, so if you're coming in for AQR, you should pick up the notes for today.
Every day.